Hello everyone, in this video we're going to show how to master even and odd proofs by doing this sort of comprehensive example. Okay, so we're going to try to prove that for a and b being integers, that a squared plus ab plus b squared is even if and only if a and b are both even. Okay, and so how are we going to prove this? So let's start by deciding what we even need to prove, right? So we see we have this if and only if statement, this biconditional. So first, we know that if we have an if and only if, we have to prove both directions. We have to prove that if this a squared plus ab plus b squared is even, then a and b are even, and the other direction. That if a and b are even, then a squared plus ab plus b squared is even. So let's write out these two directions, these two things that we need to prove. So we're going to start with the second one because this is going to be the easier one to prove. Because it's going to be easier when we start with this a and b and we want to deduce this. Okay, I just copied the statement down here and we want to show that when a and b is even, then this a squared plus ab plus b squared is even. So for this we can really just use a direct proof because we need to somehow express a and b as being even. So what does it mean to be even? Okay, so since a and b are even, what does it mean to be even, right? Well, if it's even, it can be expressed as an integer times 2, because every even number can be expressed as an integer times 2. So like 0, 2, 4, 6 is really like 0 times 2, 1 times 2, 2 times 2. So we can express these as integers times 2, both of these. We can say there exists integers, and we'll just use n and m, such that we have this a is equal to 2n and b equals 2m. So we know these are integers and they're expressed as 2n and m. And so now we want to show that this whole expression is even. So this whole expression needs to be expressed as 2 times an integer. And if we can get that, we know it's even. Okay, so let's just start with this expression as we have it, right? A squared plus ab plus b squared. And so this is kind of the format you're going to want to take with almost all proofs of even and odd numbers, because we know what a and b are, because we know they're even, and we want to show that this is going to be even. So since we know we can express these as 2 times the integers, we can actually just plug that in to our expression. So we have 2n, 2m, and 2m squared. And so now we can just factor these things in, and we get 4n squared plus 4nm plus 4m. And so to make this a little bit clearer, we can pull a 2 out and then write the rest of this. And now we see that this right here is going to be an integer. This right here is just an integer because integers are closed under multiplication and addition. So we can say that 2n squared plus 2nm plus 2m is an integer. So like a squared plus ab plus b squared equals 2 times, let's say, k, where k is an integer. So a squared plus ab plus b squared is even. Okay, so now we prove that direction, that if a and b are even, then a squared plus ab plus b squared is even. And so this is the easy direction. Now let's look at going the other direction. So let's say we started to do this direction using the same sort of approach, right? We only know that this a squared plus ab plus b squared is even, and we somehow have to deduce a is even and b is even. So if we started with the same approach and said like a squared plus ab plus b squared equals like 2n, now we would have to somehow break up this a squared and ab and b squared into a and b and find that it can be expressed as 2 times an integer. And this would be where n is an element of the integers, right? So this is going to be quite difficult. We're probably not going to want to take this approach because how are we going to somehow get this a and b where we know they're integers expressed as 2n? So what we want to use in this case, where we have the sort of larger thing on the left, is we can actually use the contrapositive and prove that. And since the contrapositive is always true when the original statement is true, proving the contrapositive proves the original statement. Okay, so what is this contrapositive? So if we had a statement, let's say we take this a squared, this whatever is even as p, and then these two being even as q. If in this case we have p if p then q. The contrapositive is if not q then not p. So we have if not q then not p. And so we have to write this in words now. Okay, so first we have this not q. So we could say, I'm going to write this a little bit still using this kind of notation. So we have if not a is even and b is even. And this little arrow thing is just saying and, implies that not p. And so that means that this statement a squared plus ab plus b squared, if it's not even, then since we're dealing with integers, then it's odd. So we can say is odd. Okay, and so what is not even and not b is even? And so when we distribute this not in, this and becomes an or. And we get that if a is odd or b is odd, then this a squared plus ab plus b squared is odd. And so proving this statement will prove the original statement. So now we have to prove this statement. But in this case, it's going to be a little bit tricky because we can't use exactly what we did before because we have this or. Last time we had an and, we knew a and b were both even, we can just say they're even. But in this case, a is odd or b is odd. We have a few cases that we have to deal with. So let's just write out the cases that we have. We could have a is odd and b is even. Right? We could have a is odd and b is odd. Or we could have a is even and b is odd. Okay, so these are the three cases, and we actually have to prove all three of these cases to prove this conditional. And so I'll write this in a bit more shorthand because it's going to be a little bit repetitive, but if we just break these up into cases, if we know all these cases are true, then we'll know that the statement is true. And we have to prove that this is odd in all of these situations here. Okay, so let's do case one. So we'll say we'll let a be odd and b be even. We know there's going to exist integers, and this backward need just says there exist, and we'll use n and m, and we're saying they're in the integers, such that we know we have to represent this a and b in terms of these integers and then plug it in, because we're going to use that same strategy that we used in the first case, or the first direction. So we're saying a is odd, so what does it mean to be odd? If even is 2n, then odd is just going to be adding 1, and that will cover all the odd cases. And then we're saying b is even, so we can represent even as we did before as 2m. And now it's just going to be a matter of doing the exact same thing we did in the other direction, where we start with the expression, and we can plug in what we described a and b as using those integers. And we get 2n plus 1 squared plus 2n plus 1 plus 2m plus b squared, which is 2m squared. And so now we can go ahead and distribute this. And now what we can do here is we see that in all of these numbers here, we have a 2 in common. And then we have this plus 1, so we can write this as 2 times everything with the 2 factored out, and then add this 1 at the end. And now we see that this right here is an integer. So this shows that we have it in this 2, let's say k plus 1. K is an integer, so we know that this is odd. So we can just say is odd. Okay, so that proves case 1. Now we need to kind of do the same thing for the other cases. So for case 2, if we let a and b be odd, then now we just have a being 2n plus 1 and b being 2m plus 1, and now they're both odd, and we can use the same steps to show that we get an odd number. Okay, and after doing all that math, we can see that this right here is an integer, and we have 2 times an integer plus 1, so this expression is odd. So finally, for case 3, we have a is even and b is odd, and we can use the same steps to show that this expression is odd. Okay, so we get that this right here is an integer. We have 2 times an integer plus 1, so this is odd. Okay, so now we've proved every case where a is odd or b is odd, then this is odd. And so doing that, since the contrapositive has the same truth values as the original conditional statement, we've proven this direction where if this a squared plus ab plus c squared is even, then a is even and b is even. Okay, so now we proved in the first example that if these two are even, then this is even, and we've proved using the contrapositive that if this big expression is even, then these two are both even. And so since we've done this, we have proved the original statement, the biconditional if and only if, by proving both directions. So this statement is true. So hopefully that was interesting. Even odd proofs are probably like some of the first proofs you'll do in like a proof-based math class, and really shows how you can use the contrapositive and direct proofs to derive some expression to show that things are even or odd. If you have any questions, leave them down below, and thanks for watching.